This problem was asked in GATE 2015, that is for 2 marks. So this is circuit given here in which we need to identify and we had to calculate the voltage across inductor and output average voltage, nothing but the voltage across the capacitor. And it is asked to calculate under the steady state operating conditions. Okay, so first of the things that we all know, during a time period of voltage across inductor in a steady state is going to be zero. So two options are eliminated here. So we are left with these two options, and we can see from the topology of the circuit, this is nothing but the boost converter. And if you calculate or if you do the volt second balance across the inductor, so that will lead us to the value of output voltage or the voltage across the capacitor which is asked. So we will do that. So during on condition, VL is nothing but the, if this switch will be on, then VL will be equal to uh, VDC minus VDC. But since this direction is shown opposite, but you can take in this polarity, so VL would be equal to minus VDC. And during off condition, this switch will be open and this diode will be conducting. So at that instant, VL would be equal to VDC minus VC. Okay. So now further, if we equate this both equation, VL 1 by T from a time period, so VL dt would be equal to 0. So that will lead to VL on would be minus VDC into T on, that would be dt, plus VL off VDC minus VC into 1 minus D into T is equal to 0. If you will equate this equation, so VC would come out nothing but the VDC divided by 1 minus D or 1 minus delta. So it is matching with our first option, so it will be correct. So moving on to the next problem. So this problem is also from power electronics, and this is a single phase full bridge inverter. VSI is given in figure, whose output frequency of 50 hertz is given, and it is using unipolar PWM technique with switching frequency of 50 kilohertz and modulation index of 0.7. And this input DC voltage is 100 volt, and L and C is given, R is also given here. We need to compute the amplitude of the fundamental component in output. Okay. However, we can easily calculate the fundamental component of VR1. That will be nothing but the M into VDC. It would be M VDC, and which is nothing but the 0.7 into 100. That will be 70 volt. Okay. Now, after computing the fundamental amplitude of voltage VR, we can easily calculate V naught by voltage division rule, and that is nothing but V the voltage across this resistance would be VR1 peak into why we are taking VR1 peak value, because we need only amplitude of output voltage. Okay, so for that purpose, we are taking amplitude of the uh, output one, and that is going to be equivalent impedance of this conductor or capacitor, that is 1 by j omega c. So a parallel combination of this circuit would be R into 1 by j omega c divided by R plus j omega c. And after that, we can take total impedance, that would be sum of this plus this. So after doing calculation, you will get the value of this much 62.75 angle minus 32.5 degree. Okay. So this question was asked in again GATE 2015 for 2 marks. Okay. Further moving ahead, this problem is based on single phase induction motor which draws 12 megawatt power at 0.6 lagging power factor. Okay. And a capacitor is connected in parallel to improve the power factor of the total system. That system consists of motor and capacitor. Okay. To improve the power factor, we added capacitor along with the motor. We all know that capacitor is used to improve the power factor along the load. So now it is assumed that real and reactive power drawn by the motor remains the same as it was drawing earlier. Okay. So real power will still be 12 megawatt and reactive power will still be whatever was drawn initially from the source, that will be same. Now we will have to see how much the reactive power delivered by the capacitor now. Okay. Now to improve power factor, capacitor, we all know it supplies reactive power. So we will see how much reactive power is supplied by capacitor. Okay. So earlier 12 megawatt power was supplied from the source, or a single phase induction motor was taking. So for that purpose, after this single phase induction motor was taking this power, and when this power got converted into reactive power, so we all know Q by P is equal to tan phi. So uh, if we know P, that will be 12 megawatt. So Q will be 12 tan cos inverse of 0.6. So that would come out to be 16 MVAR. Okay. So uh, now we know what was the initial reactive power being supplied from the source side. After that, we will compute how much reactive power was delivered by the capacitor. Okay. So now if we need to compute the real and reactive power, so uh, it is written that real and reactive power drawn by the motor remains same as before. Okay, so it will remain same as before, but how much would be supplied from the capacitor? So 12 megawatt is the earlier power, that will be same. And now to maintain this zero point 0.8 lagging power factor, how much reactive power would be drawn from the source? So that will follow the same formula, and it will come out to be 12 into tan 36.86, and that will give us the 8.996 MVAR. So now this much reactive power would be supplied from the source. So remaining reactive power will be supplied from the capacitor. Okay. So from 16, if we reduce this much power, that will be supplied from the capacitor. So now capacitor is supplying 7 MVAR approximately. So that would be answer. Okay. So this was the system. So now the remaining reactive power was supplied from the capacitor. Okay. So let us start or continue the session from the last class where I was discussing switching function, and based on that, we will continue the three-phase inverter circuit today. So let me start. I hope you remember this circuit or this Fourier series of this signal when it was conducting from minus d pi to d pi, and this was theta. Okay. So what was the Fourier series for this one? Can anybody recall it? Sorry, it was d by 2, d by 2. So let me recall it. It was d plus summation of 2 by n pi sin n pi d cos n omega t. Okay. So was it d by 2 or d? Let me confirm it. Okay.
Hello.
Yes. Hello. Who is this?
So can you please unmute yourself, sir? You are not
Oh,
audible.
oh, sure, sure. Sorry, sorry. Sorry. I was just speaking for uh, some time. Sorry. Very sorry. So, okay. So now I will continue it. Am I audible now? Actually, I was on mute, I guess.
Yes, sir. You are audible now.
Okay, thanks. So let me start the session. So now I will continue this switching function thing with a three-phase inverter circuit. So uh, today we will continue with the concept of switching function to three-phase inverter circuit where people generally feels difficulty. So we will solve 180-degree conduction mode today, and in next session we can see 120-degree conduction mode. Okay. So I hope you remember this expression from the last session. Okay. So just a second. Okay. So we are good to go now. So let me take the circuit. So I hope you would be familiar with this kind of circuit. So which circuit is this? Which power electronics converter circuit is this? Can anybody tell me? So this is three-phase inverter circuit. Three-phase inverter circuit. And this switch of first leg is H1 and H4. So generally, when H1 will on, H2 will be off. Okay. So both can't conduct simultaneously, otherwise it will cause to short circuit. Okay. So both can't be short circuited, and this DC supply would be connected to this topology of switches, and it will give us the AC voltage waveform at output side. This phase is nothing but the A and G. This will be your phase. I am highlighting it here. This will be your phase VAG, VBG, VCG.
Excuse me, sir.
Yes,
Sir, I think it will be H4 instead of H.
it will be H what? Sorry, I could not get it.
Sir, you just wrote that H2 of.
Okay, okay. Yeah, sure, sure. Thank you, thank you. Thanks. That is my H4 it is. Ah, thanks. So when H1 will be on, H4 will be off. So we can write it in an expression or algorithm. H1 plus H4 would be equal to 1. Okay. So when H1 will be on, H4 will be off, and when H4 will be on, H1 will be off. Same applies to H3, H6, same applies to H5 and H2. Okay. So H3 plus H6 would be on 1, sorry, and H2 plus H5 will be 1. So generally, if you recall from 180-degree conduction mode, if you have remembered it, otherwise you just learn it from here freshly. Okay, so if you recall or if you have remembered, you would know that H1 first conduct for 180 degree, after that H4 conduct for 180 degree, and H1 conduct for 180 degree, in which sometime it will conduct with H6, sometime it will conduct with H2. Okay, so this was the scenario there, and we all know, and this load is connected in a star form. Let us take this load is connected in a star form. So the voltage across the load should be balanced. Okay, three-phase load should be balanced. We generally consider the case for balanced load. So the condition will be there. We can write in that manner that VAG plus VBG plus VCG should be equal to 0. Agree? So after writing this, now we need to find out the switching instant or switching waveforms. So let me show you how the switching waveforms would be there. So this is your switches, how it will be conducting. So earlier H1 would conduct for 180 degree, right? And H4 would be complement of H1. So it will conduct from pi by 2 to 3 by 2. So this total duration is 360 degree. Okay. So for 180 degree upper leg switch H1 is conducting, and for remaining 180 degree H4 is conducting. Okay. Now the second phase, we all know in three phase, all the phases are shifted with 120 degree. So when A phase, let's say VA angle 0, VB will be angle minus 120 degree, and VC will be equal to plus 120 degree or minus 240 degree. Okay, so this is scenario here. So here also for conduction of phase B or second phase, it will be shifted from H1 by 120 degree. Okay, so that's why I have shifted it 120 degree from H1. So this is the waveform of H3, and it is shifted from H1 by 120 degree. So it is conducting from 2 pi by 3 to 5 pi by 3. Okay, so now it will be very easy. Since we know the Fourier series of this one, okay, we know the Fourier series of H1. We can easily write uh, what would be the Fourier series of H1? Can anybody help me to write it?
Sir, D into V naught.
But here no V note, so we can take it as a 1. Just it is a switch, no voltage source. So yeah, you are correct. It will be D plus 2 by N pi sin N pi D cos N omega T. Okay. So now we know D, right? Do we know D? How much is the value of D? D is equal to how much?
So pi by 2 divided by the whole time period.
Yeah, means pi by 2 minus pi by 2. Pi by 2 minus pi by 2. divided by 2 pi. So that will come out to be half, right? Since it is conducting for 180 degrees, so we can take duty cycle to be half. Now we will put it in this equation. Okay. So H1 would be equal to half plus 2 by n pi sine n pi d. Okay. Sine n pi d. D is half cos n omega t. Okay. So this will be Fourier series of first switch. Okay. Why it was necessary to compute Fourier series of first switch? You might be wondering. So let me tell you. If you need to compute this pole voltage VA0, right? VA0. If you need to compute this VA0 and when the switch H4 will be off and H1 will be on, let me take this figure to here. Just a second. Huh. So we can write VA0 is equal to H1 into Vs, right? Any confusion? Similarly, we can write VB0 is equal to H3 into Vs. If we know the Fourier series of H1, we know the Fourier series of VA0 indirectly. We just need to multiply with Vs. Again, if we know the Fourier series of H5, we can calculate VC0. Okay. But generally, we need to calculate the value of either phase value of output voltage or phase value, oh sorry, or line value of voltage VAB. We will be asked either VAG, VBG, VCG, or VAB, VBC, VAC. Right? Our aim is to calculate these values. Okay, but this step will help us to land there, right? Now I am extending this concept further. If any doubt till now, you can ask me.
Sir, clear.
Fine, thanks. So now I will take one switching instant. Let us say I am taking uh, this H1 would be on from first phase. From second phase, H6 would be on, this one. And from third phase, H2 would be on. So there are several instances where different switch combinations will be on. I'm just taking one switching instance. Okay. Means if they are conducting, so we can say upper leg switch is from only A phase, right? And two lower leg switch is conducting. Means there will be conduction on VAG. If this switch would be on, so then current will flow from VA to Z, and lower switch is closed, H6 and H2, and this current IA would come out from this path and this path. Okay, so this is a switching instance where we need to identify the voltage and current, right? So VAG would be how much? VBG would be how much? And VCG would be how much? That we need to identify to understand this, right? Now, let us say all currents are same and all impedances are same. Okay, generally this is the scenario for balanced case. Uh, let us say IA is equal to IB is equal to IC is equal to I, and Z1 is equal to Z2 is equal to Z3 is equal to Z. Okay, so to balance all the voltages VAG plus VBG plus VCG is equal to 0. So uh, yeah, so when I is flowing through this path from G to B through H6 to supply, so this would the voltage drop would be here IZ, voltage drop would be here IZ. Okay, so this much voltage drop should come from from A supply, since it is the positive terminal. So it will supply to I, right? If I current is going this side, I current is going this side. So 2I will come from A supply or upper leg switch. So if let's say VAG is equal to 2IZ, okay, and VBG is equal to minus IZ, since our default current direction is this, then only we can say IA plus IB plus IC is equal to 0, right? So if we say this, IA plus IB plus IC is equal to 0, then IZ and IZ, this both current will be supplied from the first leg. Okay. Now, if we do VAB, now we need to find out the line voltage VAB. So VAB, can I write in that manner? VAG minus VBG. Definitely, I can write it in this manner. Okay. We know VAG, we know VBG. 2IZ minus minus IZ. Okay, so it will come out to be 3IZ. So this is the line value of VAB. Now, after doing that, we have to compute, and this VAB value would be similar to VS if this both switches would be closed, VAB, when only A and B would be closed. So let's say VAB. So this value would be equal to supply. Okay. So that's why I can write it here VAB equal to VS. Okay, so this step is just to help in our derivation. Now I again want to write VAG in form of supply voltage, because we know only what is supply given from the source. Okay, so VAG was 2IZ, so we can write it in terms of VS, so it will come out to be 2 by 3 VS. Okay, again, if we want to write VBG, it was minus IZ, that would come out to be minus VS by 3. Again, VCG would be equal to minus VS by 3. I hope no doubt would be there. If any, please ask.
No, sir. Clear.
Yeah, thanks. So we have come to a point where we know the value, instantaneous value. Mind it, it is instantaneous value because we are taking an instant of switching. We are not taking account of all switching actions. Okay. So this is an instant where we are doing it. Okay. So at this instant, this voltage value would be in such manner. Now we want to go ahead and we want to compute all the values of voltages in line phase with all the harmonic component. Okay. Now we told you VA0 is equal to H1 into Vs, right? I told you here VA0 is equal to H1 into Vs, right? Now VA0, can I write it in that manner? VAG plus VG0. This voltage would be, if you apply KVL, that would come out to be, I am taking this path, okay? VAG plus VZ0, okay? So this node would be connected to this node, okay? So this if this G and 0 would not be connected, then it is known as a floated neutral. But here it will be connected, and we can write as VA0 to VAG plus VG0. So this information will lead us to another important thing. Similarly, we can write VB0 is equal to VBG plus VG0. Again, VC0, we can write VCG plus VG0. Okay. Now we will use this information again. So I want to add all the voltages VA0 plus VB0 plus VC0. I will write VAG plus VZ0 plus VBG plus VZ0 plus VCG plus VG0. That would give us VAG plus VBG plus VCG plus 3VZ0. Okay. We knew this voltages. We wanted to compute these voltages, but we need VZ0 in terms of H1, H3, H5, or so on, right? We have simplified till this point. Okay. Again, one basic information will come in use. If the load is balanced, it will come out to be 0. Agree?
Yes, sir.
Fine. Then we have computed VZ0 in terms of VA0 plus VB0 plus VC0 by 3. Okay. Now we know VZ0. Now VA0 we knew H1 VS, VB0 we knew H3 VS, VC0 we knew H5 VS. Okay. So now we can write VZ0 in terms of VS by 3 H1 plus H3 plus H5. So this will be our VZ0. Okay. To compute VAG or phase output value of the inverter, we needed this VZ0 very desperately. We will see we as we concluded VA0 was VAG plus VC0. So now if I need to compute VAG, I need VA0, and we just calculated VG0 from this expression. I will simply put now all the values in terms of H1, H3, H5. So we will get VAG is equal to VA0. VA0 was nothing but H1 VS minus VG0. VG0 is VS by 3 H1 plus H3 plus H5. And after doing this jugglery, we will write simply VAG as a Vs by 3 2H1 minus H3 minus H5, right? So we computed VAG. If we know the switching function Fourier series of H1, H3, H5. So now you might have realized that why that Fourier series of switching function was very important. And if you just know this Fourier series of H1, you can easily shift H3 by 120 degree, and you can easily shift further 120 by H3 to H5. So that was it. So now I will write the expression of H1, H3, H5, and I will put in VAG, and you will get Fourier series of the phase value. Fine. So VAG was Vs by 3. Let me again write H1, H3, and H5. H1 was D, which is half, plus 2 by n pi sine n pi d, which is again half, cos n omega t. Okay. H3 we can write half plus same, just shifted by 120 degree, 2 by n pi sine n pi by 2 cos n omega t minus 2 pi by 3. Similarly, I can write H5 as half plus 2 by n pi sine n pi by 2 cos n omega t plus 2 pi by. Okay, so we just computed H1, and this H3 and H5 just come out by shifting, right? Now, if you want to compute H4, let's say, okay, if you want to compute H4, H4 would be just, we will apply this condition. We knew H1 plus H4 is 1, then H4 would be 1 minus H1. So let us see what will be H4, 1 minus H1. H1 was half plus 2 by n pi sine n pi by 2 cos n omega t. Okay. So after doing further simplification, it will come out to be to infinity 2 by n pi sine n pi by 2 cos n omega t minus pi. This minus pi is coming due to this negative sign. We just wanted to convert this negative sign to positive sign. This is your negative. We just wanted to have in very simple positive form. So we did trigonometric identity, and here this will be expression. It will be shifted by pi from H1, right? Even from signal analysis, you can see here this. Where did it? Okay, just a second. This waveform H4, it is shifted by pi from H1. Okay, so from H1 also you can directly write H4, but this is the algorithm of H1 plus H4. Now we almost know all the Fourier series of all the switches. Now we just need to put all in one place, and we are good to go. So we said that VAG is this much. Let me take it. We know now VAG is Vs by 3 into 2H1 minus H3 minus H5. We know H1, we know H5, we know H3. Okay, we know H1, H3, and H5. Now, we will just put it here. So VAG is equal to Vs by 3 to 2H1. Okay, 2H1. 2 into half plus summation n is equal to 1 to infinity 2 by n pi sin n pi by 2 cos n omega t minus, this was 2H1 minus H3. Again, I will write H3 as half n is equal to 1 to infinity 2 by n pi sin n pi by 2 cos n omega t minus 2 pi by 3. I hope you are not lost in all these expressions. These are very simple. You will realize. Yeah.
No, sir, these are simple. I'm getting it.
Yeah, thanks. Yeah. So this was H3 and again H5. You can write 2 by n pi sin n pi by 2 cos n omega t plus 2 pi by. Okay. So this was all H2, H1, H3, H5. So here, if we see carefully, this 2 into half will get cancelled out from this two terms, right? This half in minus, this half in minus, so minus 1, and this plus 2 into half, so that will be plus 1. So this DC term will be get cancelled, and that's the behavior of your inverter output voltage because that is AC. So DC had to go away, right? So that's why, and from expressions also you can see that this DC term is cancelled now. Now what is left we will collect here. So VAG is equal to Vs by 3 to why not we take sin n pi by 2 as a common if sin n pi by 2 is everywhere, right? If sin n pi by 2 is everywhere, so we can take it as a common. Okay. So n is equal to 1 to infinity and n pi by 2. After getting it common, whatever will be there, just 3 cosine function, nothing else. This will be 2 minus cos n omega t minus 2 pi by 3 minus cos n omega t plus 2 pi by 3. Okay. We have arrived till this point, and this, even if you leave it at this point, it would be sufficient. Okay. If like anybody ask what will be the fundamental component of VAG, okay, what will be fundamental component of VAG, you can easily write from this point Vs by 3. We just take n is equal to 1. We will put n is equal to 1 here, 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 here. So sine pi by 2, which will be 1. So that I can write it like that. 2 cos omega t minus cos omega t minus 2 pi by 3 minus cos omega t plus 2 pi by. So now This is your fundamental component. You just need to compute this trigonometric identities and you are good to go. And let me solve this trigonometric identity for you. So these two terms are common. One is minus 2 pi by 3, one is plus 2 pi by 3. So I will solve it for you here first. 2 cos omega t minus, okay, the summation of this cos omega t minus 2 pi by 3 plus cos omega t. Let me write one more step. Minus 2 pi by 3. Now we all know cos A plus cos B is equal to 2 cos A plus B by 2 cos A minus B by 2. Okay. So we will do it here. This calculation 2 cos omega t plus 2 pi by 3 omega t minus 2 pi by 3. So it will come out to be omega t, right? Cos A minus B by 2. So this omega t and omega t will be get cancelled. It will be cos 2 pi by, right? It will be equal to this. This is nothing but cos 120 degree, and cos 120 degree is nothing but the half, right? Half. So now we will plug this value in this expression. So that is Vs by 3 into 2 cos omega t minus, yeah, sorry, it was minus half, right? Cos in second quadrant it would be cos would be minus, right? So minus half into 2 cos omega t. So we have come out at conclusion that is nothing but the 2 cos omega t minus minus plus, so plus cos omega t. So it is your 3 cos omega t into Vs by 3. And if now you see here, your Vs cos omega t is the thing. So I hope everything is fine till this point. Have I done any mistake? Yeah, I have done one mistake. I left this component 2 by n pi, 2 by n pi from everywhere, right? So I should have multiplied 2 by n pi, and here I should have multiplied by 2 pi n pi, right? Are you getting it? Where I committed mistake?
Yes, sir.
Yeah, so that would have multiplied, and it would come out to be 2 by pi. It will be multiplied. So sorry for the mistake. I hope you should not get confused. This 2 by pi is multiplied. So now the fundamental component of VAG1 is 2 Vs by pi cos omega t. So all the purpose of doing switching function is to arrive at this point. So this is your fundamental. You can do similar thing if you would ask any other component, VAG3 or VAG5. All phase voltages are same, right? You just need to put n is equal to 1, 3, 5, and one step at trigonometric identity to solve it. And after that, you are good to go with your phase values. Right? So I hope it is worth it to compute phase value of inverter output voltage of 180 degree. At home, you can try and you should try for 120 degree, right? For
Yes,
120,
so one thing I wanted to ask is, can I use all of this that you just taught as a journalized method to find any of the function like voltage or current in gate exam, or is it specified to some of the cases?
it is true to everywhere, right? In for any signal, you just write this Fourier series. If you know this D and duty cycle of any signal, even let's say any signal is given like this, okay? First, the first thing you will do, you shift along the origin, okay? You know after shifting what expression will be changed in your expression, right? If we have shifted from here to here, you just need to do omega t plus theta, whatever theta is this. After that, you know the Fourier series of this, okay? It will be from something, anything, pi by 3 to pi by 3. You know how to calculate Fourier series expression of this waveform. After computing Fourier series of this waveform, you just do at the end this shifting. Actually, we have done here this simplification for entire power electronics converter. Either it is buck converter, boost converted, AC, rectifier, DC. If, like, let us say, during last class, mm, I told you that this is some voltage, right? Vs, this was some voltage, and this was load. Okay. So when this switch was getting closed, then you were getting V naught is equal to H1 Vs, right? So this is nothing but if you take average, it will be dVs. You are getting DC value, right? You are getting DC value. Now, what if I just replace this DC voltage with AC voltage? Let us say if I do here Vs sine omega t. Okay, so you will get it here Vs sine omega t. Okay, so whatever you change here, that will reflect, and you can analyze any circuit. And slowly we will see, even for DC-DC converter, even for rectifier, we will see. But the most complex thing was inverter. So I just wanted it to sort it out. If you get confidence on inverter, you will be easily able to solve any kind of converter circuit. So my answer is yes, you can apply this expression to any signal or any switching circuit or any waveform. This is very generalized. Got it?
Yes, sir.
Fine. So I think time is up. Actually, one step was left. I just wanted to conclude the line value VAB. So should I continue or should I continue it in next class?
So you can continue this line.
Okay, fine. So I will show how to compute VAB or the Fourier series of VAB from this VAG expression, whatever we have computed. So let us go ahead. This expression is very, very important. Even just you know H1, H3, H5, you can come up at this conclusion, and after that, everything at your fingertip. So now we know VAB is equal to, in line value, one very good thing is that you do not need this phase voltage, right? But you can always verify it from phase voltage side. Let me again bring the converter circuit. It would be convenient to have that circuit. Okay, here it is. Huh. I know VAB. Sorry, I need to compute VAB. Okay, so VAB, can I write VA0 minus VB0? Fine.
Yes, sir.
VA0 was nothing but H1 into Vs. VB0 was nothing but H3 into Vs. Fine. Our job is simplified at this point only. We know H1, we know H3, Vs is given. We just need to do the expression jugglery. So Vs H1 minus H3. Again, we will do Vs H1 was half plus half I am using because in 180-degree condition, our conduction period is 180-degree out of 360-degree. So duty cycle would be half. So that's why I am writing directly 2 by n pi sine n pi by 2 cos n omega t. This is for H1 minus H3 half plus 2 by n pi sine n pi by 2 cos n omega t minus 2 pi by 3. Again, we can cancel this DC and DC component. So what we will be left with Vs summation n is equal to 1 to infinity 2 by n pi sine n pi by 2. This much is common. Cos n omega t minus cos n omega t minus 2 pi by 3. Now, this was VAB. Okay, this is Fourier series expression of VAB. Now, let us say we need to compute VAB1 again, the fundamental component of VAB. Again, we will put n is equal to 1 everywhere. 1, 1, 1, 1. So 2 by pi Vs, okay, cos omega t minus cos omega t minus 2 pi by 3. Okay. Again, we know cos A minus cos B is equal to minus 2 sine A minus B by 2. Sorry, yes, no. A minus B by 2 sine A plus B by 2. So we will do that, and that will lead us to, I am just solving this step here. That would come out to be minus 2 sine A minus B by 2. So cos omega t minus omega t, that would get cancelled. It will remain 2 pi by 3 by 2. Okay. A minus B by 2. So this 2 will get out. And sine A plus B by 2, omega t plus omega t, 2 omega t minus 2 pi by 3 by 2. Okay. So further, it will lead to minus 2 sine pi by 3. Sine pi by 3 is root 3 by 2 sine omega t minus pi by 6. Okay. So we can cancel it here. It will lead out to be 3 sine omega t minus pi by 3. We solved only this portion here, and this portion is already simplified. So VAB1 would come out to be, let me show you, 2 pi 2 Vs by pi into minus root 3 not Vs again, sine omega t minus pi by. So this is your fundamental component. Let me rearrange once again. 2 root 3 by pi Ps sine omega t minus pi by 3. So this is your fundamental component of VAB1, right? Was it easy or not?
Yes,
And
sir, we just need to do it carefully, otherwise it's
yeah,
right.
you just need to do this trigonometric identity very careful. And we can verify it from phase value. Phase value was 2 Vs by pi cos omega t, and line value is multiplied with root 3. And we all know in a star connected, phase value is multiplied with root 3. And some angle difference between phase and line of fundamental will definitely be there. Similarly, you can compute for third, fifth harmonic at your own. Then you will get expertise in at this topic. And at the same time, however, we will discuss 120-degree conduction mode in next class. But you should once try with your own help, right? You should just practice it at your side, so you will not get any confusion or anything. It is very simple. Just you need to derive all the expressions very carefully. So I hope you got it. Any final doubt before we wind up the session?
No, sir, it's clear, and I'll just try to derive it and then I'll ask.
Sure, definitely. Yeah, thanks.
Thank you, sir.
Thank you. Thank you.